Welcome to the talk. I'm Qingqing Cao from Stony Brook University. I'm happy to present my research, efficient and practical neural question answering for heterogeneous platforms. Deep learning NLP models power many applications like Siri, Alexa, or Google and Bing search. These models are growing bigger and more effective, but they are also causing more deployment challenges. It's difficult to run large models on resource-constrained mobile devices. It's also hard to run them in a faster and practical manner. Bigger models consume much more energy on battery-powered devices and increase costs in cloud servers. My research aims to bring together NLP and system research to address these challenges. Next, I'll first talk about how to run question answering systems efficiently on mobile devices. Think about using a QA service like Siri, but without sending personal data to the cloud providers. One way to do this is to put deep learning QA systems on device so that the QA models can directly answer user queries using on-device data. But the problem is that deep learning-based QA models are often large and complex. They don't even fit into a smartphone memory. And even if they do, they run extremely slow. We designed a DeQA system that can run neural QA models on the device. Given a question, the QA model needs to process many documents to give an answer. Guided by principles from the system research, first, we can reduce the amount of data processed through the QA pipelines. To do this, we designed an early stopping classifier to dynamically decide how many documents are needed. Second, we look into the QA models and find that the document processing competition is a bottleneck, and they don't depend on the question. Therefore, we can pre-compute the document processing offline. We also design memory optimizations like moving the embeddings of QA models to a key-value database. With DeQA optimizations, we successfully reduce the QA latency from over a minute to under 5 seconds on a smartphone. QA model research is a moving target. Over the years, the NLP field has shifted to a new paradigm of models called transformers. Next, I'll talk about how to make transformer models run more efficiently, not only for mobile devices, but also for cloud servers. Transformer models are growing exponentially larger and cause significant resource challenges in deployment. Part of the DeQA idea cannot be directly applied here, because the transformer model processes the question and document together. We approach the problem using the insights from NLP research, and we show that for transformer models, the question and document have less dependence in the lower layers, so they don't have to be processed together. We designed a decomposition technique called DeFormer that breaks this kind of lower layer dependence by processing the question and the document individually. Now we can push the document processing offline and just do lookout during runtime. This can improve the inference latency by 3 times and reduce 70% runtime memory. Additionally, we develop efficient NLP algorithms to close the accuracy gaps to do the decomposition. Notice that DeFormer only makes minimal changes to the transformer, so we can reuse the pre-trained transformer weights and avoid expensive repeated pre-training. As you know, big NLP models are expensive. Next, I'm going to talk about how to measure the cost by studying the energy consumption of NLP models. The NLP community recently started to look at how to measure the energy consumption of NLP models. One simple way is to combine the energy consumed by the hardware components based on the utilization. However, this solution is insufficient because the system research has shown that there are complex energy interactions like power lag or tail energy. And non-utilization behaviors like data movement in GPU memory can cause energy bottlenecks. In our ongoing work, we take a holistic view of how the NLP models interact with the hardware systems. Driven by the NLP domain knowledge and system research principles, we combine the NLP model abstractions together with this hardware resource usage and view them as a proxy to estimate their complex energy interactions. So far, I have worked on 3 projects to build efficient NLP systems. Now, I'd like to introduce 2 exciting research directions for future work. One promising direction is to incorporate modalities beyond text. For example, on-device visual question answering can help visually impaired people without privacy issues. Most of my existing research has focused on inference. Another interesting direction is to make training more efficient. For example, designing novel NLP algorithms that can learn faster and use less data. Thank you.